Good morning. In this session, I would like to demonstrate another example of using equation-oriented approach. By now, you might have got the concept of using equation-oriented approach in Aspen. To the best of my knowledge, no such features oriented approach are available in any other process simulator. But you might have already observed the limitation of switching over to equation-oriented approach. You must be in a position to solve the problem at least once in sequential modular approach. Now let us see, this problem can also be solved using design spec. So let me show you how to solve this problem using equation-oriented approach. In fact, the only issue equation-oriented approach is identifying appropriate variables from the variables available in your simulation. Once you are able to do that, the problem should be very simple. Now we are using, it is cooled by cooling water from 100 to 70 degrees Fahrenheit. So the outlet temperature of cooling water cannot exceed 65 degrees Fahrenheit. So we need to calculate what is the flow rate of cooling water in order to limit this temperature increase with respect to the cooling water. So let us try to deal with this problem. So the two components we are handling in this problem are benzene and water. So let me define those two components. So having defined these components, you can go to the property selection method, choose a property, go to the next step and choose the simulation environment. So let me take a exchanger, heat exchanger. Heater model will not be able to identify the other things like the utility. So you need to use a model for solving this problem. Let's say this is your process fluid, cold fluid, sorry. This is your hot fluid. So in our case, the hot fluid happened to be benzene, the cold fluid happened to be toluene. Benzene in and benzene out. And this is cooling water in, water out. So having drawn the flow sheet, now let us try to define the problem. To use the system of units. So this is benzene is entering at 100 degrees Fahrenheit pressure. So you can assume atmospheric pressure is not mentioned, say 14.7 psi. And benzene is entering at the rate of 50 lb moles per hour. So go to the next. Now cooling water is available at 50 degrees Fahrenheit. We assume the pressure as 14.7 ambient conditions. Remember, in order to complete the problem definition of rating, we need to specify the water flow rate. In fact, we are required to calculate. So let me also assume this as 50 lb moles per hour, right? So this is required in order to complete the problem definition for rating. So we have defined both the input streams, and then we would like to specification is the hot stream outlet temperature, sorry, the benzene is cold stream outlet temperature should be at 70 degrees Fahrenheit. So we have provided all the required input, so we should be able to run the problem in sequential modular approach, because by default we are using sequential modular approach. So let me run the problem in sequential modular approach once. You can see the stream summary. So we got the outlet temperature 100, so this is 70, but sorry, cold water is this one. No? I think I made some specification problem. So benzene in, this specification is cold stream outlet temperature should be, no, this This is hot stream outlet temperature we want. Hot stream being benzene, it is at 100, but it is hot stream outlet temperature is to be 70. So let me reset and run the problem. Now you can see benzene is entering at 100, leaving at 70, and the cooling water is entering at 50, but the outlet temperature happened to be 91 in order to cool benzene from 100 to 70. But the requirement here is we need to have maximum temperature to be at 65. Of course, if you want, you can use a design spec to solve this problem, but let me go and try to solve this problem is using equation oriented approach, having solved the problem at least once in sequential modular approach. Now, the moment we do this, as we have seen, you can expand this EVO configuration and create a spec group, new. So let us give the specifications. What is the requirement for us? We have seen from the previous results that the outlet temperature was 91 with respect to cooling water. So cooling water outlet temperature, which has been calculated as 91, we wanted this to be at 65. So I'll select this variable. User spec is instead of calculated, I wanted to provide this value as input. Value is 65 degrees Fahrenheit. The type of variable is temperature. Units degrees Fahrenheit. Right? So we have converted one variable from calculated to constant, and we would like to convert one variable from constant to calculated. Remember, we have started with an assumption of cooling water flow rate as 50 lbmols per hour. So let me see that benzene in not benzene, cooling water we want. Let me go to 50. Yeah. So this is benzene, cooling water input. Remember, this is also calculated. What we want is constant. Benzene mole flow 50 lbmols per hour, which has been provided as input in the earlier case. So I am selecting this variable, and the spec is constant. Now I will convert that into calculated. So in other words, specifying the variable outlet temperature of cooling water, we are trying to calculate the flow rate of benzene that gives us this required temperature. So this is mole flow. The variable is mole flow. Units lbmols per hour. Having created this spec group, now we should be in a position to run the problem in equation-oriented approach. You can see it took a very little time compared to the sequential modular approach, so we should be able to observe the results. So we got to the required outlet temperature of cooling water as 65, but what was the flow rate of cooling water? I should have selected not benzene, so this is the problem. I should select the flow rate of cooling water. By mistake, we have selected flow rate of benzene. Water in cooling water flow rate, water mole flow. This is the one that we need to select, 50. Now calculated variable units lbmols per hour. Now you can see the results. See the mole flows of water in order to get to this required temperature of 65 is to be 139.748. So only when you use the cooling water at this rate, we will be able to limit the temperature increase from 50 to 65 in order to cool benzene entering at the rate of 50 lb moles per hour from 100 to 70. So with this, I would like to close the session.